And away we go. All right. Greetings once again. Hello, everybody, and welcome to our Unit 7 review over differential equations. We only have one more unit left. I can hear you guys cheering all the way from across Avon that you're excited about that. So we'll have one more Zoom review session that will focus on the topics before the Unit 8 exam. And then after that, you're actually going to get Zoom bombarded. You're going to have an offering just about once a week, a shorter one. This won't be nearly as long as these unit reviews, but about a 45-minute session that will focus on one central idea common to the AP exam. And you're always welcome to join those live or watch them delayed at some point. So the focus tonight is obviously on this idea of differential equations, and we've got two different documents that we're going to be taking a look at. And the first document actually is the review guide itself that has kind of a hodgepodge of things on it. And I know that some people may have dove sort of headfirst into this when I passed it out. I noticed some kids yesterday working on problem 1, which I was really kind of happy to see right away, because I think problem 1 itself has got some tricky aspects to it. So I wanted to run through this one quickly as a warm-up, and then we can start taking a look at various other problems all over the place. Actually, we can look at some of the ones on the Big Ten and then take some questions out of you. So in the future, our Zoom reviews will be not necessarily always on Tuesday night. In fact, I think I'm going to actually talk to you guys in class and make a decision on what nights work best. And I'm open to anything. I'm gonna assume that Friday nights and Saturday nights probably aren't the best, but we'll talk about what would work with most people's schedules. So we'll take a look at that. So for this number 1, we've got some separating to do, right? This problem is almost borderline a problem that we may not be able to solve, but fortunately for us, we have the lovely 0 here. Had this guy been anything but 0, that could be problematic, because our first step is just going to be to add the y prime over there. And as you add the y prime, there's nothing wrong if you want to change the y prime notation to dy dx, because you're going to have to do it anyway. Now, I'm going to do something here that might seem kind of funny, but a lot of times, we're so used to the dy dx being on the left side. That's okay. Make it happen. All you have to do is just sort of spin this thing around like it was on some axis at the equal sign, and now you have the dy dx on the left side. And you don't have to do that by way of like subtracting this over and subtracting the 2xy plus 1 over, because that's going to make everything ugly and negative. We don't want that to happen. So at this point, you can divide y plus 1 over to the left. So he would be underneath the y, and the dx that's underneath this fraction is going to multiply over to the right. Notice my little trick about leaving a little space there. And now we are all set up to be able to integrate both sides. So we're going to put the integration symbol here. We're going to put the integration symbol here. And then we're going to say, hey, which side would you rather do? If it was me, I would pick the right side. I'll do the right side, and I'll make you guys do the left side. In fact, the right side's easy. The integration of 2 would be 2x to the second over 2, which that's just x to the second. And we'll put our plus c here. But I wanted to discuss this whole left-sided business because it's been a while since we've done some advanced integration techniques, and I just want to put this on your radar. I'm not making any guarantee about this happening tomorrow or on the test Thursday, for those of you taking it Thursday. But you've got a situation that you're just going to have to remember that if the degree of the top of a fraction and the degree of the bottom either match, or if the top is larger than the degree of the bottom, and we must integrate that, we always have to do division, right? There's really no other recourse. So off to the side over here, I'm going to make sure I have plenty of space, write it up here. We're going to have to take y, and we're going to have to divide that by the denominator, which is y plus 1. Okay, it won't take very long to do this division. It's a pretty easy one. So we think about y and how many times y would go into y. Well, that's not too complicated, right? Y will go into y only one time. So y plus 1 times the 1 is going to result into y plus 1, of course. And when we subtract this, And by the time we subtract this, it will be very clear that our remainder is going to be -1. And what we do with the remainder is we always write it over the divisor. You could think of this as adding -1 over the divisor, but you might as well just say subtract, right? Adding a negative is just subtracting. And so we'll put that 1 over our y plus 1. And so it essentially, what we are trying to do here in problem 1 on the left side is integrate the result of this division. I'm going to write it over here to do sort of our off to the side work. Okay, so that is what our left side was equivalent to. Hopefully that makes sense. And please let me know. We got a little smaller group tonight. Let me know if there's anything that you need me to repeat in the chat. Just mention it and I can kind of go over that if you're not real sure of the process. So the integration of 1, of course, is y. And the integration of 1 over y plus 1 we've seen a million times is minus, in this case because of the minus sign there, natural log absolute value of y. So that's what we're going to stick over here on the right, on the, the left side. Okay, so again, I'm not making any predictions about will you see long division. Honestly, it's more likely than not that you won't see it, because it is a very unusual integration technique. But I just want you to file it away, because I have a feeling that it's going to pop up on the AP exam at least one time, and I don't want it to surprise anybody. Okay, this particular problem asks us to find what's called the general solution. So that means that we do not have a C to find. That means that we leave C in our answer, and then the debate that we have to go through is, hey, do we solve for y or do we not solve for y? The problem didn't state so, and typically that won't be something that you worry about on the test, because if you have a free response problem, if it wants you to solve for y, it'll tell you solve for y, much like I have done already on some quizzes. And if it's a multiple choice problem, you're going to be able to tell if you solve for y by looking at the choices. Are the choices all solve for y? In this case, for this particular problem, we are done. I guess I didn't need to use all this space over here. I had all this space right here. What was I thinking? But we are done. And the reason we're done is because this particular expression is so, this equation that is so complicated because of the presence of y outside of a natural log and a y inside of a natural log. It's very difficult, if not impossible, to get y by itself. So that's all that needs to be done here. Okay. Let me take a look at one more problem off the review, and then I am going to turn the focus to the Big Ten. I notice we've already got a few questions, or at least one question on the or about at least the Big Ten. You guys, I'd like to take a look at number 6 here, if that's all right. This is off the review guide. Think about the level of sophistication of some of these differential equations. You know, you guys are starting to see some really pretty impressive ones. And I compared these with some ones that have appeared on the recent AP exams, and you really are operating on a little bit higher level than what the AP exam questions are. So I'm really pleased that you guys are doing a good job with that. For this particular problem, we're going to think of this y prime as being dy over dx, as always. And again, if the dy over dx on the left side is really bugging you, or being on the right side, I should say, is really bugging you, then you could just take one quick moment and spin this around. So we'd have x times y times dy dx equal to 1 plus x squared, quantity 1 plus y squared. Okay, after this, we say the y's stay on the left side. So I'll have a y divided by 1 plus y squared dy, that's occurring on the left side. And then if I divide an x over to the right side, I have 1 plus x squared all over x with a dx there. Okay, we multiplied the dx to the right. Hopefully that separation is agreeable to everybody. And then we integrate both sides. And I guess one of the purposes of me doing this particular problem is to illustrate the differences in these two integrations. They look similar, except they're kind of reciprocals of one another. So on the left side, we have to think to ourselves, hey, what kind of integration technique is happening here? And the answer, a lot of you hopefully are thinking the same, is U substitution. And I don't mind writing a step or two if that's going to bother you. I think on the review guide key, which is actually now posted, I don't think it was posted until this afternoon, but the key, I don't think shows the nuances of the integration. And I know that I've already had a kid or two ask about a particular integration that occurred on the Unit 7 review. And the reason why I didn't write the U-sub information, it wasn't because I think that you're above that and you don't need to see that. It was really more of an issue with space, the amount of space that I wanted to devote to the solution. So if our u is 1 plus y squared, that means the derivative of u is, of course, 2 times y dy. So you go through the whole process of thinking, yay, we got the y dy. We're happy about that. We're not so happy about the 2, but that's an easy fix because we just offset with the 1 over 2. And then we look at this as being just a 1 over u form now, right, with respect to u. And that, of course, is going to result in the natural log of the absolute value of that u, which in this case is 1 plus y squared. Now, I don't think I needed absolute values there because 1 plus y squared is positive all the time, but you have to really make sure, you guys, we all know that these absolute values eventually go away. Almost every problem, well, every problem we did remove them, but that doesn't mean that you don't write them here, because you could and will take a penalty if you don't put the absolute values in this integration when they are needed. This is just the lone exception that they wouldn't necessarily be needed here. Okay, now on the other side, remember our discussion about the division. If you have a situation where your fraction has a larger degree on top than on bottom or equal, you would use division. But this particular problem doesn't need long division because you only have one term on the bottom. So you can just call this 1 over x plus x squared over x, also known as just x to the first, and we can find that very easy to integrate. Okay, if by some chance you had forgotten that this breaks apart this easily and you like went down a path that used long division, you will get the same answer. You might feel a little foolish afterwards because you didn't need to do that, but it's going to be the same. So here, notice I'm putting the absolute values around the x because now it's absolutely required. That x could take the risk of being negative, and I don't want that to happen, not in a natural log. And then the x has to integrate to become x squared over 2, and then we have our plus c, of course. All right. Now, at this point, if you recall, my strategy is to find this value of c. In fact, I will do that typically before I even multiply through by a constant. There's nothing wrong if you partially solve for y. In other words, you've multiplied everything through by a 2. That c can absorb the 2, and then you can solve for it. You guys could even put a 2 in front of the c and still get the correct answer, because there's going to be so many variations of how you guys find the c, but depending on what you do, we're all going to come out to the same answer at the very end. So let's say I leave this as it is, and I use the initial condition, which is 1, 0, right? The ordered pair, x is 1, y is 0. So that would give me 1 half, natural log of 1, I believe, right, equals, let's do that again. Yeah, natural log of 1, 1 plus 0 squared, equals natural log of 1 again, plus 1 squared, which is 1 over 2. So when we dive into this, we find out that, whoa, this is going to be a 0, right? This is going to be 0. So when you solve for c, you get c equal -half. And if this is a free response question, you've just picked up another point. Okay? Now, I don't know if anybody has the key out. Maybe you're kind of comparing my answer with the key or what have you. My key is different, and I did this on purpose. My key says that c is -1. but I wanted to show you the variation. The reason why my key says -1 is because I did multiply by a 1/2 across before I found the C, okay? Now my key also has our items on opposite sides, so that's a little bit different. Or wait, let me double check, you guys. Forget everything that I just said in the last 5 minutes. I need to edit that out. I was looking at problem 5. I'm sorry. In this particular problem 6, the key does say C is -1/2. Hopefully that didn't confuse anybody. Just forget what I said. That's what you guys do most of the time anyway. Just forget what I said. All right. In that particular problem, I did not multiply through by a half. I could have, and that would have given me a different answer than the C, but it would have been in the long run the same. So now the next question that we need to address is, do we solve for y? Well, let's go ahead and replace the C first and then take a good look at what we have. Now here I'm going to live life on the wild side, and I'm not going to write the absolute values because I don't need to. And then over here, if I replace the C with -1/2, I'm going to be looking at something like this. And at this point, do we really want to solve for y? Well, if I multiply through by a 2, I can get the ball rolling, I guess. And 2 times the natural log of x appears plus x squared minus 1. And you'll notice that my solution key stops roughly right about here. In fact, my solution key doesn't even get rid of the 1/2. This problem it's very possible to solve for y, and one of the reasons why I chose this one is to give you that extra little step or two to show you what it would look like. Again, I think it was probably just time and room as a premium, so I decided not to. But if we went to that route, let's see what happens here, guys. We could exponentiate both sides. We end up with 1 plus y squared on the left, and on the right side, this is where the magic happens. You see this 2? This 2 is going to decide to move. He's going to become the exponent of the x, right? We are allowed to do that. Now, if I do that, I want to make sure that I delete this 2. All right, so he physically moved in that spot. And that was really important because, because I'm not going to be able to get rid of this e and the ln otherwise. So what do we got going on here? We got a mess. That's what we got going on here. So let's go ahead and we'll start to split this right side up. Maybe e ln of x squared times e to the x squared minus 1. There really is no need to split this apart. You can, but you're not going to gain anything because we want this e to the ln part to be isolated so that I can just call this x squared. I know I'm kind of running down a little bit into problem 7 here. So 1 plus y squared actually is x squared times e to the x squared minus 1. Now at this point, it's kind of getting ridiculous in terms of what this thing is going to end up simplifying to, but it's possible that you could subtract 1 from both sides. And there we have it. And then to get y alone, it's possible that you could square root both sides. In the home stretch now, guys. And then the decision that you have to make, do you put a plus or do you put a minus there? And that's a really good question because it's typically determined by the sign of your y. But your y is 0. It's neither positive nor negative, so we really don't have any kind of clear-cut vision as to what we should do here. And I think that was a very big impetus as to why I chose to not solve for y in the review guide. You're not going to see situations like this that force you to solve for y, okay? I don't want to put a plus or minus here because then I don't have a function. Right? So it's sort of like I've got this point that's in limbo, and to be honest, I'd probably have to use some technology and graph this thing to really get a better handle on what I should call the y. Okay, so please don't worry about that because that is not going to bother you guys. All right, I'm going to catch up here a little bit with the chat. But Caitlin's asking, is kecked, so if you have a kecked problem, you can start from there on the test, just like you do the integration and automatically, and that is true. If you notice a story problem that says the rate of change of y is directly proportional to y, then you can start immediately with y equal kecked. You won't lose any credit by making that your first step. But I will tell you, without question, that kind of problem will be multiple choice. All right, you don't have a full, just normal kecked problem that's going to be a free response. So if it's multiple choice, I'm not going to grade your work anyway. But all right, let's go ahead and turn our attention to the Big Ten. That doesn't mean that we're completely done with this review guide if other problems and questions come up. In fact, I thought about reviewing a slope field just really quickly before we finish tonight, because I'd hate for you guys to miss any points on a slope field question, because they're typically going to be really easy. So Big Ten, Big Ten, Big Ten, yay, Big Ten. Where are you, Big Ten? Where? All right. It's a loaded. Checking the chat to see it's just us. It's just little Olivon still. Okay, doesn't matter if we jump around on this a little bit. I did have a request from Ryan to do part F towards the end here, so let's start with that guy. Whoops, F, right here he is. This is a great question, Ryan. This question almost stumped your teacher when I officially first saw this. This is a really good one to look at, and I'm not again making any wild predictions about the test in terms of this kind of problem. I want you to be turned on to this one and kind of get an idea, because I noticed that a couple of years ago there was a free response question that had a part very similar to this. Thank goodness it was only worth 1 point. A lot of my students didn't fare real well on that particular part, they said, but they still did fairly well on the problem as a whole. In fact, even some of my best kids were fine getting an 8 out of 9 on this problem. But there's definitely a little bit of a trick to this, and if you've looked at the skill builder solution, it maybe give you a little bit of insight into what was really going on. So the question says, you got a non-separable differential equation. Okay, stop, wait, what? Non-separable? What the heck are we supposed to do, right? We can't solve it. We can't do anything with it. I can't get the x on one side and the y. It says it's non-separable, and it truly is. But it says that it has a linear particular solution of a form that looks like a line. And we are asked to find the sum of the slope and the y-intercept. Well, I'm confused here. Doesn't that sort of imply that we're supposed to solve this? I mean, I see y by itself. That looks like it's solved to me, but how can you solve something that you can't separate? And that's where the dilemma is. But this is a very potent word here, the idea that the first derivative is linear. Because if the first derivative is linear, I'm going to ask you to think about this. If we were to take the second derivative, all right, and again, I know you're thinking, what? Why would we want to take the second derivative? Well, bear with me. If any first derivative is linear, right, what does that say about the second derivative? Okay, well, let me read that again. If the first derivative, and it's not that the first derivative is linear. I need to rephrase that. The first derivative's solution is linear. So this y is linear. If you take two derivatives of that y, where do we go? That's the question that I wanted to pose to you. Maybe that makes a little bit more sense. So, for example, if you have y equal, let's just make something up, 3x minus 5. What do you guys think that the second derivative of that's going to be? Well, the first derivative is going to be 3, right? And then the next derivative of 3 is going to be 0. Okay? So the second derivative is 0. Now, why is that a big deal? Well, if we go back to this dy dx and we take its second derivative normally, kind of like how we took a second derivative working that lizard problem today, and I know we had a question about that in the chat. I'll address that in a second. You can take a second derivative, right? You can take a derivative of a derivative with respect to x, means you would get 8 like normal, but then the derivative of minus 2y would be minus 2, but you got to tack on dy dx. Because this is a variable y, it's not an x, so we have to use that idea of implicit differentiation. All right, now the trick, if this second derivative is equal to 0 and this same second derivative is equal to 8 minus 2 dy dx, what does that mean? They both equal one another. That's the trick with this, you guys. Now, it might be, again, kind of confusing to see, well, what comes next? Well, you want something like this for your final answer. You want something that has like a y in it and an x in it, maybe a constant number b in it. Right now we have an equation that has a dy dx. We have another differential equation. Well, if you remember, what does dy dx equal? Well, dy dx is 8x minus 2y. So if you make that replacement and then go ahead and simplify this, distribute the 2, or I should say distribute the negative 2, and then proceed to solve this for y. So I'm going to swing this around. I'm going to put the 4y on the left, and I've got negative 16x plus 8 on the right. I'm just going to have them trade places. And then I'll divide by y. I get y is negative 4x plus 2, right? And here's your m. Here is your b. And what is m plus b? Well, I sure hope it's, my signs are jacked up, aren't they? My signs are, wait a minute, my signs aren't jacked up. What did I do wrong? 8 minus 2 times 8x minus 2y. I distributed a minus. Looks good, looks good. You're right, you guys. When I swung this around, I was kind of careless. If I were to keep the 4y on this side, sorry, I do have to add 16x over. There, I added it. And I have to subtract the 8 over. Now I can spin it around. I'm sorry, you guys. But you know what? I did this on purpose. I did it on purpose because I wanted to show you that if you end up getting a nonsense answer on a Big Ten, that's why it's a Big Ten, right? You're able to check your answers. You know you did something wrong. So we don't want the plus and the minus in that arrangement. We want it like this. So we have positive 4 minus 2, which obviously creates 2 as the result. So you can cross that guy off. Okay, but yeah, Brandon, Jason, you are exactly right. That's what went wrong with that problem. All right. I like this question. I really do. I don't mind telling you, no, you don't see this on the test. This very likely may come back again in one of our mock exams, though, because that problem that I was kind of alluding to is going to be on one of the mock. I think it's the second one, if I'm not mistaken. Okay, so we'll see if you guys remember something like that. Okay. I don't know if you guys have any ill feelings about the lizard problem. I think there was a lot of good things going on with it. The idea of using the second derivative and whatnot. I want to see real quickly if that's kind of on your mind. Is there a problem closely associated with that on either the Big Ten or the review. Just give me a second here. I'm kind of looking to see what might best suit you guys. I'm going to tell you, the review guide is really primarily concerned with just solving differential equations with a little bit of slope field. I think we're going to turn our attention more to the Big Ten. And is there another second derivative on that guy? I'd say I is probably the best one, but it's not quite asking the same thing that the lizard question did about over approximations and under approximations. But I wouldn't mind doing the I on that if you guys want to take a look at it. I think, Caitlin, you may have had a suggestion to do I. So let's take a look at that one. It's the only one that sort of requires a calculator, and it's not because it's some really complex kind of thing. It's just that somewhere in this problem, I think you have to like multiply 24 by 14. And I figured, that's kind of a tough deal. So let's let you use the calculator. But outside of that, it's doable without a calculator. So we'll read it. It says, on the time interval 0 to 3, the number of weeds in a large garden is given by the function w that satisfies this differential equation. At the time 2 days, there are 20 weeds in the garden. We want to figure out what is the second derivative of w with respect to t when w is 14. So it's not a separate and integrate, right? We would really be wasting our time if we did that. And it's kind of funny, you guys. I'm going to laugh. Not at you. I'm not going to laugh at you guys. I would never do that. But I would laugh at me. If I were to like separate and integrate this, we have enough information. Right? You want to make really clear, we have enough information. We could find W. We could find an equation for W very easily in terms of T. But if you look at your question says, find the second derivative. What that means is we just went the wrong direction, right? We went up, we integrated up to get W. Now we have to take two derivatives down to get the derivative that we want. So if we're already standing or staring at the first derivative initially in the problem, why don't we go ahead and work from that, right? And you're going to find out that there's some information in this problem that we don't even use. Okay, so for this second derivative, if nothing else, to get some more practice with differentiating with implicit type of procedures, we would say 1/12 is a constant. We can drop him straight down. All right. Now we take the derivative of negative 318, which is 0, right? I'm okay. You want to plop that 0 in. That's fine. Now the derivative of 24w. Well, normally the derivative of a constant times a variable is just the constant. But keep in mind, this variable is not the same as this t, right? So we're taking the derivative of w with respect to t. That means you have to put a dw dt right here. Okay, so that's what your second derivative is. Now, it asks you to evaluate this when w is 14, but that doesn't mean that the 14 is plugged in for the dw, right? We have to figure out what is this dw equivalent to, preferably something that has a w in it, so that we could plug the 14 in. And lo and behold, we don't have to go much farther than what's written directly above. We're going to replace the dw with that differential equation, which is much the same thing that we did when we did the lizard problem, which is on the 7.8 homework skill builder. So the 1/12 drops down. I really don't see any need to write the 0 plus anymore. So I'll take 24 and I'll multiply that by 1/12 quantity negative 318 plus 24w. Close the first parenthesis, close the second parenthesis, and oh my gosh, there's 3 parentheses here, aren't there? Wow, that's a lot of parentheses. All right, so now we can actually go about our business in finding this result when w is 14. All right. So there's some things that we can initially do here. I'm going to keep the 1/12 out in front for just a moment, and then I'll take the 24. And since these two things are just really quickly being multiplied, we're allowed to call those a 2 as long as that 2 gets distributed, right? We still have to distribute this result in to this binomial. Okay, let the negative 318 sit out there and wait. And then here we go, 24 multiplied by 14. Remember how I said we have to do that? Well, you know what? In the time it's going to take me to get my calculator software loaded, I could probably solve this by hand. Plus, I'm getting old. I need some multiplication practice, right? Keeps the mind sharp. Okay, boy, I hope I did that right. Otherwise, that would be quite embarrassing, right? So I think we get 336 out of that multiplication there. And I guess we still have to take negative 318 and add 336. But I want to say that that's just equal to positive 18, is it not? So you have 1/12 and then 2 times 18, and then things are going to start to fall into place really quickly here. 2 times 18 is 36. Divide by 12. And remember, your final answer has to be a whole number, right? That's really a great thing about these Big Tens. And I'm really grateful that I have a friend who's really creative and can write these. It's really great to self-check, and if obviously you don't get that whole number, you just need to kind of go back to the drawing board and figure out what may have gone wrong. So all right, okay, no problem. Hopefully you guys got a little bit out of I anyhow. I'm not so sure at what point where we need to take a look at your next. I really enjoyed working through problem A this morning or today in school, but anybody, is there a few people in the chat that are in period 3? I kind of forget sometimes. Anybody period 3? Caitlin's in period 3, yeah. And Brandon. Okay. I tell you what, and Abby, okay. For the three of you, we did not do this problem at all. Am I right? We did not do anything with the Big Ten in period 3 today. Okay. And I think it was because somebody in period 5 had asked about them. And then I went ahead and made sure that those two problems I recreated for period 5 and 6. So I tell you what I am going to do, and I know that some of you have already seen this, but I can go through this somewhat quickly. I want to do those two problems again really quickly for those students. So if you didn't understand A, and I think the other one was C, I'm going to work A and C for those folks, okay? So if you have A and C memorized backwards and forwards, go grab a sandwich, right? Bring me one, and then come back, and then we can kind of pick up with some new stuff for you guys. So for part A, it says, consider this differential equation. Let y equal f of x be that particular solution with the initial condition 3, -1. Your directions are to find the equation of the line tangent. All right. Now, we're going to write it as y equal mx plus b, and then we are going to find the b. Now, when you read through this, you want to make sure that you're very conscious of the fact that you do not have to solve this differential equation. There is nothing about this question that says we need the solution to the differential equation. You're going to write a tangent lines equation. That's what it wants you to do. Okay. The two things to write a tangent lines equation is, number 1, you need slope, and number 2, you need a point. We are doing really good in the point department. Right here we have it. We don't have the slope, but this is a calculus class, and we know that slope means derivative. And what better way to express a derivative than dy over dx? So if you guys can find what is this value of dy dx specifically at the point 3, -1, you'll have your specific slope. And all we need to do is replace the y with -1 and replace the x with 3. So there we have it. If you simplify the numerator, you get positive 3. And if you think about the cosine of 3 pi, and I'll do this the way that you guys are more used to. I'm going to use the unit circle. I think you guys kind of like it better anyway. So the unit circle, if you go around one revolution, that's 2 pi, right? And if you go around another revolution, you are at the point negative 1 comma 0, sorry. And then don't we know that the first coordinate is cosine and the second coordinate is sine? Okay. Hey, if that doesn't work for you, try the Mr. Record way, right? Try the way from 1937, and that's when you just graph a cosine curve, which kind of looks like this, and I'm going to stop right there because that's one cycle at 2 pi. That would be half of that first cycle at pi, right? And I kind of started to go through another cycle, but I only go as far as 3 pi here because that's where it stops, and that happens to be at negative 1. So that's another way to kind of think about how these two sort of interact together, the unit circle and the graph. So we end up with negative 1 here as our denominator, so the slope is negative 3. And then we just write the point slope formula equation, right? Y minus negative 1, which is y plus 1, equals the slope negative 3, quantity x minus 3. And then if we want this as y equal mx plus b, then we'll go ahead and we'll subtract 1 over. Meanwhile, I'm going to distribute this negative 3. And then if I combine like terms, basically the negative 1 and the 9 will add, and I get an 8. And that's what I'm looking for. I'm looking for the b value only. It better be a whole number. It is. So we have the 8, and that would have been the first number that you would have crossed off if this is where you started the Big Ten. Okay. Now, let's go ahead and take a quick peek at number C, or letter C. And let's kind of understand the same idea, is that consider this differential equation. Okay, yeah, hey, I know we can separate, we can solve it, but let's read because we may not have to do that. It says let y equal h of x be that solution. Okay. There's the initial condition. The question, find the limit of that particular solution. All right, you got me. We are going to have to find the solution to it, right? This is not just writing in a tangent line or anything. We have to do the full-blown solution. But luckily, this is a pretty easy one, right? If you divide the y over to the left, got it? Multiply the dx over to the right. Now be conscious of the fact that that x squared is still in the denominator, right? This is like 1 over x squared. Actually, I lied. It's like 2 over x squared, isn't it? And then we put the dx after it. Now, you guys probably are aware this 2 could have divided over with the y, and you could have had a 2 in the bottom. I don't advocate that. If you think logically down the road, your goal is to get y by itself. So why would you want stuff in front of the y early in the problem that you can get rid of and move to the other side? Plus, it makes it just a little bit trickier to integrate. All right, so keep those constants on the x side. Integral symbol, natural log absolute value of y equals. On the right side, do not call that the natural log absolute value of x squared. You may get slapped. So think of this as, if you just kind of dream. This is 2x to the negative 2 that's being integrated. So the 2 drops as a constant. The x raises a power, and then you put the negative 1 power also below it. And this thing looks like a hot mess right now, but kind of clean it up a little bit. You just got yourself a negative 2 over x is all. Okay. Now the c can be found by plugging in 5 over e. And I know that the 5 over e is a very unusual thing to plug in, but there's a reason for it. If I didn't use 5 over e there, this Big Ten wouldn't have a very clean answer of a constant whole number, and that had to happen. So the x is going to get replaced by 2. So we find that this negative 2 over 2 is just a negative 1. So if I add it over, c is going to be 1 plus the natural log of 5 over e. Okay. let's go ahead and rewrite that equation. ln of 5 over e, I'm sorry, not that equation, this equation, the one with the dot, ln of absolute value of y equals negative 2 over x plus 1 plus ln of 5 over e. Now, in order to be able to take the limit of h of x, which is y, this y has to be by himself. So exponentiate, exponentiate. The absolute value of y would normally be what we have here, but what's the sign of the y value? It's definitely positive, so we can remove the absolute values and not worry about any like negative sign on the right side. And then over here, well, what do we have over here? Well, over here, I'm going to say we have e to the negative 2 over x plus 1 power, and then that plus there can drop as a times as long as I use another base of e. And that's kind of nice. It's kind of helpful because the e and the ln here are touching, so the 5 over e is going to replace all of this. And to be honest, it looks better if I just write that out in front. So this is about as friendly as your y expression can be. Yeah, there are probably other ways that it can be written, but I don't think it's necessarily going to be simplified any better. So let's just see what we got. So we're supposed to take the limit as x gets really big of this thing. Okay. And we would be doing this without a calculator, just so you know. This doesn't have a calculator icon by it. Otherwise, you guys would just whip that TI Inspire out, right? I know you. I know what you guys do. So let's let x get super big. So picture this number here, super large, like 2 over a billion, 2 over a trillion. That's going to cause this to become very small, like 0. And negative 0 doesn't change the fact that it's still 0. But, oh, you're going to add 1 to 0. So what that basically means is that we're taking the limit. Well, it's not really a limit anymore because we've invoked the x being big. But what this really means is that you get 5 over e, right, multiplied by e to the, what's 0 plus 1? That's just 1, right? Well, I'm glad that these e's are going to disappear because we don't see too many e's in our box up here, do we? And of course, they cancel. And that is what allows us to call this answer a 5. I really like that problem. I like the fact that it can be finagled so that you can get a whole number between 0 and 9. Okay. You know, the first question people are going to ask, is there a limit question on the test? Well, there could be. I don't think that this is necessarily outrageous. It's nice that I can try to vary the test a little bit. I don't want it just to be solve the differential equation over and over again. I will say that that is a pretty large part of the test, but for the most part, you know, the byproducts, the sort of secondary kind of questions are going to be things that we've seen. All right, you're not going to have to dig down too deep. You're gonna have had some exposure to them for sure. Okay. I'd like to flip over, if you guys wouldn't mind, back to the review guide. And I want to make sure that you guys are pretty confident with drawing in some of these slope field equations and whatnot. Now, number 9, yeah, I laughed at this one. I wondered if you guys were just going to like, oh, just like all the names that you were going to call me under your breath, because it's got a differential equation, right? dy dx equals x minus 1. And it says in part A, create a slope field for this differentiable equation using what? Did I read that right? 25, right? How many of you are really mad at me right now? Just say yes. It's okay. You can say yes in the chat. Is 25 unreasonable? That's a lot of points, isn't it? Okay, there you go. Jason, you're honest. Good. I know that seems overkill, but you guys, if you really look at the differential equation, it's not that bad. I wouldn't give you 25 to do if it was going to take forever. And because you only have the presence of x in this problem, it's going to make things move very quickly. And we can just start from the right side. Let's do that. That's when x is equal to 2, correct? All along this vertical strip. So if x is equal to 2, what's the derivative each time? Well, 2 minus 1 is 1. So all you got to do is just draw some point or some little slope segments that kind of look like they have a slope of 1. So bam, there's 5 of them done that fast. Okay, what about when x is 1? What do you got there? 1 minus 1 is 0. So these 5 are going to have a slope of 0. We're 2/5 done, right? We're 40% done. If you let x be 0, 0 minus 1 is negative 1. So draw little slope segments that have negative 1 as their intended slope. And now we're 60% done. So I think I've got you convinced that this moves fairly quickly. Negative 1 minus 1 is negative 2. Now this time, what do you guys think? Is that probably about the direction that we want to go? So I'll just try to draw. What? W? What? Go Cubs. All right, so back. This one's not going to go away, is it? All right, so got to watch what my hand is leaning against here. So we're going to go ahead and try to draw slopes of negative 2 like that. And then when we come to negative 2 for the last x, that's a slope of negative 3. So we're kind of looking at something that would have this kind of steepness, right? Basically, what I would look for in this problem is just to make sure that you have the correct negative slopes, you have the correct positive slopes, and the correct zero slopes. And I know that you have a slope field problem on your exam, and I don't mind telling you that it has 12 points. I believe there are 12 points, and they're very clearly defined. It's not like the quiz that some of you had some complaints about finding those points. And it really won't take very long for you to find the slopes of each of those 12. I want you to take your time, but I'm going to reward you heavily for it. Because it's got 12 points, I'm going to give you 3 points out of 9 on a free response. So that will be a third of the value. And you guys, you should kill that. Right? Just take your time with those. Don't rush. And that should be a very easy 3 points. Now, I'll tell you the other part of that problem. It only has 2 parts, an A and a B. The other part is a 6-point differential equation that you'll separate, integrate, and solve. So knowing, how good you guys are becoming at that could be a very, very successful problem for you. Okay? But I wanted to make sure that the slope field was done now so that we could look at part B. And part B says to sketch a solution to this differential equation that goes through the point negative 1, 1. Okay, so we first of all locate negative 1, 1. I'm going to use a different color to highlight that. So that would be right about yonder, right? And the thing that I want to emphasize here is that when you draw the slope fields, you don't have to give me a Vincent van Gogh or a Da Vinci painting. I don't have to have something that's, artistically beautiful. You just have to draw something that is definitely decreasing, because that's kind of what these slope fields are indicating. And as the slope fields start to get less steep, my hope is that you would see that these would be decreasing and concave up sections of the curve. Over here, you have a horizontal tangent line, so it's very likely that could serve as a relative extrema, maybe a relative min, because we're going to end up going back to increasing when we look at those slope segments. So you would draw something that would eventually look something like this. Okay, now as far as how precise do you have to be, guys, as long as you go through that point, I'm happy. You have to go through this point though. So there's a point of credit being awarded or taken away if you don't go through the initial point. The second thing that you have to do is make sure that your graph extends all the way to the farthest edges of the coordinate plane. Even if you don't draw arrows, and you can see here that I did not draw arrows, it's okay, but you have to still extend it. Now, if you draw arrows, that's fine, but it's not required. A student that does this and draws an arrow there would not receive full credit. I know that sounds kind of silly because it's like, well, what does that mean? Isn't this kind of going that direction? Well, it's not my rule, guys. It's College Board, ETS. It's the Test Development Committee people. It's the question leaders, and I support them. I think let's go ahead and abide by the rules that they set forth. Okay. Any kind of other variations with this? I mean, you know, what if somebody drew something that maybe was a little steeper? Like, what if you drew this? I would count that. I would have no problem with that. I want to make sure that you guys at least make it look like the minimum is happening when X is 1. This thing that I graphed in red doesn't quite look like that, but to be honest, it's close enough that I would have given you credit. Okay, if you drew something, I'm going to erase this orange one. If you drew the orange one so that maybe it was not quite as skinny, it was like a little bit more opened up, more rounded. I don't want to use blue. Let's use orange. If it looked like this, that would receive credit. All right, it just has to be a parabola that opens upward, that passes through that indicated point, has this vertex or min pretty close to what I drew here. I know it's kind of hard to make it perfect, and extends all the way to the farthest edges, right? You're going to be safe. Okay. The rest of this problem is finding the equation of a tangent line, which we've already done a couple of times today, but you would just plug -1 in for x, and you'd have a slope of -2, and then you just use your point slope formula there. That's all. And then I think you're supposed to use that result to estimate f of 0.3. Hopefully that makes sense. It probably takes me 2 seconds to finish this. So your answer would be y minus 1 equals -2 quantity x plus 1. I do believe that is the answer. And then if you want to get y by itself, you can. You're going to probably do it eventually here in part D. So if I were to multiply through by the -2, and then if I add 1, this would be the best looking, hey, I've got y by itself answer. And then f of 0.3 is just basically saying to you guys, take this answer, -2x minus 1, and we'll use it as an approximation of this 0.3. Okay, and we would have, I believe, this, which is what? What the heck is that? -0.6 minus 1. I almost feel like I need a calculator here. That's -1.6, right? -1.6. You know what's kind of neat here, you guys? If I can like get rid of the stuff on my graph, let me show you what's going on here. Let's get rid of these orange things. Probably the best looking, trying to think, the best looking graph that I could draw that goes through -1, 1 probably is that red graph. But just to give you an idea what's going on in this part C, if we draw the tangent line at that point, -1, 1, now I'm freehanding this, so bear with me, guys, bear with me. It's going to be freehanded here. Maybe the slope, the tangent line looks like that. Well, I want to show you what happens here. If you're estimating what f of 0.3 is, f of 0.3, okay, 0.3 is, I don't know, guys, is that about right? Is that about where 0.3 would be located? Let me scroll up here a little bit. 0.3. So, yep, I don't know what the y value is on the curve because I haven't solved for the curve. All right, I'm just kind of guessing about where that red curve would be. But if I take it all the way down to the line, yeah, if I take it down to the line, does that look like it's about -1.6? Boy, it does now, right? It really does now if I kind of cheat and, yeah, make my tangent line look more tangent. You see what I'm saying? I didn't draw the tangent line perfectly, but if I make it look probably more realistic as a tangent line, maybe if it behaves, there we go. Maybe now I probably could have you convinced that this does look like it could be indeed negative 1.6. Okay, and another cool thing about this problem is that it does have another part to it. If you haven't noticed, there is a part DE, a part E, which is the part that you guys have been doing forever and ever and ever that you're pretty good at. And this is actually having you solve the differential equation. And if you look at the answer key, I'm not going to solve this because this is a frightfully easy one. But if you solve it and get y by itself, the key says this is the answer. Well, it would be very interesting if you guys plugged in 0.3 for x. It would be. The answer would probably be fairly close to negative 1.6, but not exactly. But it would be probably within about 1 unit or so. And then if you kind of think back to the problem today that we did in class with the lizard weight, isn't this kind of a similar situation? Is this tangent line here an under or over approximation for the curve? You guys are welcome to type that in the chat. Is it under or over? The tangent line, under or over approximation for the curve? All right, we have 2 answers. Everybody's asleep, aren't you? All right, maybe everybody's just agreeing, right? So it definitely is an under approximation. It's an under approximation. And if I asked you, okay, well, why? Well, you can't say because the picture says so, right? The reason is really because this curve is concave up, but you would never be asked to verify that unless you were actually taking the second derivative. And I'm not saying that we can't take the second derivative, because I think we can take the second derivative. You know what? You want to know how easy the second derivative is? Let's do it. Second derivative. Bam, done, right? What's the sign of that second derivative? It's always positive, and it's positive for any value of x that you plug in. That means that we're always concave up, because I'm pretty sure that this is going to be a parabola solution, so it's always concave up like that. But it is going to kind of verify our findings. Positive second derivative, concave up curve, slope of the tangent line is going to be or the tangent line, sorry, is going to be an under approximation. So doing good there, guys. All right. Hey, I'm going to open it up to questions, because I honestly, I've covered everything that I wanted to make sure I covered. But I am free to do whatever you guys really want me to do. And even if that extends to a Khan Academy question, if there's a way that you can share one with me. By the way, just so you know, for period 3, 5, and 7, your Khan Academy has been reassigned, and the due date is tomorrow night. So you guys will have that extra day. I know that seems to be a little bit not in line with what period 6 has to do, but for period 6, yours is going to go ahead and be due. I tell you what I'm going to do. Period 6, I am going to go in right now. I'm going to make yours due tomorrow night as well. Okay, that way everybody's got the same number of evenings to have done the lesson. Obviously, it's kind of, maybe it's not necessarily besides the point, or I guess what I'm trying to say, it's not a waste of time, I guess, to do Khan Academy after the test, because you guys have a big test coming up in your life, right? The AP exam. So, and I totally get that. So I'm going to go ahead, and if it will let me, will it let me? It's not going to let me. It's assignments. Assign. Here we go. So period 6, and just so you have proof, I'm going to show you this. Period 6, I'm going to go into differential equations, click it, and I'm going to assign. The 36 just means that there's 36 activities. That includes the videos and stuff. And make it the same questions for everybody. And yours is now due March 4th, 11:59. So it'll stay open until that time. Okay. I think I may have mentioned before that I try to give everyone the same amount of time on Khan Academy, regardless of when your test is. Hey, spring training, guys. Serious exam. Okay. Where'd the chat go? Chat. Oh, Anthony, great question. I didn't even think about that. In the chat, Anthony asked about the Khan Academy. The answers that are all slope fields, how do you want us to write that out? Do you have to draw all the slope fields in your notebook? Okay, how mean do I want to be here? No. Yeah, you guys, please don't do that. I would give you like a mulligan on that. On the slope field questions, I don't see how you guys can probably practice those online, you know, unless you had a tablet PC. So let's go ahead and kind of give you guys a little reprieve from the slope fields. As far as like if there's any problem that has you sketch a curve though, I would say you could go ahead and sketch that curve on paper, but you don't have to put the slope segments in that were already there. So that'll definitely save you guys a lot of headaches. Okay. And again, I'm kind of standing by if you guys have any other questions. It's possible we could even end this a little early. I didn't think that this one was going to be 90 minutes, just because of the focus was very narrow on this stuff. I honestly think you guys are pretty good at this. If the question about the lizard weight bothered you, go back and look at that again, and just maybe try to redo it without looking at the work that I showed. And I think that will be really, really beneficial. For those of you who might be here that's in 7th period, we will review that problem tomorrow in the 7.8 homework. So. All right. Again, anybody got anything? Yeah, let's take Jason's question here. Jason asked about ln of 150 minus ln of 350, which I believe, wasn't that like a problem that happened on like the quiz, right? On the quiz that we just had. If you see something like this, it's likely that you're at least going to have to consolidate these two into one single logarithm. And since this is a subtraction, you'll go ahead and use division. 150 over 350. That's the bare minimum of simplification. Now, if you notice that 150 over 350 does reduce, that's like nice. I mean, you can just write some easier numbers. I think it's 3/7, right? Because you can take out 50 out of each one. And so that would be what I was looking for there. If, oh my gosh, guys, heaven forbid, yeah, this won't happen. If it was ln of 150 plus ln of 350, what would you do there? Yeah, that's not good, is it? That would be a multiplication problem. I'm going to show you a couple of things just to kind of verify these findings, because I think some of the stuff was taught so quickly to you guys in college algebra, and I know that with my students, I tried to reinforce it by just showing you some really quick calculator sort of verifications. Not that meant to be a proof or anything, but I always think that if you guys see some calculator reassurance, that you kind of at least know it's a thing. So if I come on, all this done, good. So if we take a look at just really quickly the ln of 150 minus the ln of 350 on the calculator, hopefully with any luck this will simplify it the way that we were thinking. Now, yeah, the other one, this would be a fun time. This would be good. What is this? What's the calculator going to say? Yeah, it says what I thought it was going to say. It actually did multiply those. I just didn't want to multiply them by hand. So those are the two kinds of simplifications. So, okay. All right, let's take a look at number 17, Brandon. Not a problem. So we're going back to the full review packet. And 17 is the last problem. And it's a Newton's law of cooling. So if anybody that may have missed Monday's lesson, I know there's a few of you that were out Monday. Maybe this kind of will help you guys a little bit. Newton's law of cooling will make one appearance on the test. It's a multiple choice question, and it's not one that you necessarily have to solve. All you have to be able to do is just recognize the components of it. So, for instance, if I said that, I'm trying to think of something that's not too terribly morbid, but let's come up with something here. Well, let's do this. Let's say that there was a murder. I know that's not real fun, but there was a murder, and the person was shot in an alley, and it was a 70-degree night, like in a kind of a cool spring night, 70 degrees. What would the equation be that would depict the rate of change of the temperature of the body? Okay. And let's say that the temperature of the body when it was shot was, let's guess, it was 98.6 degrees, right? That's what all of our temperatures are traditionally. So a 98.6 degree body shot, left in an alley in a 70-degree night. Well, what Newton's law says is that the rate of change of the temperature of the body with respect to time is directly proportional to the temperature of the body minus the surrounding ambient temperature, which I told you was 70 degrees, right? Now, notice that when I said that the body was 98.6 degrees, that has nothing to do with the setup. The initial temperature doesn't help at all with finding the equation. The initial temperature does get used eventually, like when you solve this and have a C in it, okay? But that's the kind of question that I'm talking about on the test this week. You've got a scenario as a multiple choice problem, and it just says which of the following 4 choices is the correct version of the Newton's law. Okay. Now, that being said, I still want to do this problem. We got time, and it's not going to be terribly long to do the solution. It's just a good general practice anyway. But it first of all says we have a differential equation. You guys, I have no idea why there's a 1 there. I don't know if it's a typo, if I just haven't gotten rid of that, but you don't need a 1. It doesn't change anything. So that models the temperature above room temperature of an electric burner. T is in degrees Fahrenheit. Time can only be in positive or 0. So it says find a general solution. So the first thing that we do, we solve this by separating the variables. Now, the 14 minus the 0.01 t has to travel together. And I think sometimes that tricks students. You can't add the 0.01 t over and expect to make any headway in trying to solve this. So you have to do the whole thing as a package deal, divide it over, and you've got your capital T on the left, and you multiply the d little t to the right, and now you have a separable differential equation. You have something that you can now do the integration of both sides for. Okay, now this integration is definitely one of the trickiest ones. That's why I probably held this off for number 17. U is going to equal 14 minus 0.01 t. The derivative of that U is negative 0.01, right, with respect to t. And if I multiply the dt over, basically I see that I do have this dt present, which is good, but I don't have the negative 0.01 present. So you have to offset with the reciprocal of negative 0.01. Do you guys know what the reciprocal of negative 0.01 is? It is negative 100, right? Think of this as negative 1 over 100. Flip that upside down, you have negative 100. And now you have to think about the ln of u, which is ln of the absolute value of u. So it would look like that. And then that would be equal to the integration of 1 with respect to little t would be little t, and then there's your plus c, you guys. So this definitely has a little bit of a weird thing that goes out in front, but it's nothing that we haven't at least talked about before. And it does say solve for t, and it has to stay as a general equation. So I would definitely divide both sides by 100 first, or negative 100, because I want everything away from this natural log before I start exponentiating. So there's the left side now. Here is the right side. Notice how the c will just chew up the negative 1 over 100. And now if we put an e here, if we put an e here, the e and the ln knock each other out. 14 minus 0.01 t. Now, you can probably imagine absolute values, they're going to go away for all the same reasons. And we're going to probably see why a little bit more when we get to the end of the problem, but they're not needed. And on the right side, we can call this e to the negative 1 over 100 t, or I could put the t on top like that. That's a little bit more convenient, times e to the c. Now this times e to the c, if you remember, if we call all these guys little subscripts here, basically what that means is that this thing could become just a plain old c out in front, like that. And now to get the t by itself, we would subtract 14. So there's the negative 14 plus this sort of version of ce to the negative t over 100 with a negative 0.01 t on this side. And then I would, probably to get rid of the 0.01, I could divide by 0.01, but dividing by 0.01 is the same as multiplying by 100. And I'll take the negative along with it. So if I multiply this left side by negative 100, I have t by itself. And if I multiply negative 14 by 100, I have negative 1400. And then if I multiply the c, e to the stuff by negative 100, I could have the c absorb everything. I don't have to, but you could. All right, I would grade both ways and I would give credit for both ways. Okay, and I know that seems kind of confusing for some of you, but trust me, it still works out. Okay. When the burner is turned on at time 0, the temperature is 0. We can use that fact to find the value of the constant. So we're going to say the temperature, capital T, is 0 when the time, little t, is 0. So that gives me 0 equal to negative 1400 plus CE to the 0 over 100, which is just e to the 0, which is 1. And so you find that C is 1400 here. Okay, now remember what I said a moment ago? If you did not absorb that negative 100 into the C, that would have come out in the wash because you'd have had a negative 100 here. And then by the time you plugged in 0 and solved, you're going to get the same result. Okay, so everything's going to work out. The last, is there just one part of this? It says the safety standards board determines that this type of burner, if it's left on, is unsafe if its temperature can reach 1500 or more. Is this burner safe or unsafe? Actually, exceeding means it goes over 1500. So the thing that you would have to do with this problem is understand that this is a limit question, right? If you leave this thing on continuously, that's implying that we're going to let time go on to forever. So if we take that t equation, which remember it's up at the top of the screen, negative 1400 plus the c, which is positive 1400, e to the negative t over 100, what does this thing become? Well, let's see. Let's let this t grow to be really big. I would have a large number divided by 100, which is still going to stay large, and that negative is going to make it negative and large, right? Which just basically means that this e is going to find its way in the denominator looking like that. Agreed? And e to the infinity is huge, but if it's in a denominator, that tends to approach 0. Am I right? Okay, so I have basically, what do I have here? I have something that largely doesn't make sense again. Let me check my key, guys. Why is this guy is supposed to be positive, guys, because this doesn't make sense, does it? If this becomes 0, like I'm saying, how could our temperature be negative 1400? That's cold. Somehow that 1400 was supposed to be a positive, but is that, oh, it's because I'm a dum-dum. When I multiplied both sides by negative 100, right, isn't this what we're doing? Multiply this by negative 100, multiply negative 14 by negative 100, let the C absorb. I forgot to see that those two negatives cancel, guys. So it's an easy fix. There's no negative there, there's no negative there, and no negative there. So the most that the temperature will reach, the hottest that this plate will ever reach is 1400 degrees, which means it's safe, right? And when it says justify your answer, the justify means that we showed a limit, right? Justify your answer is very different from like explain your reasoning. So, okay. So, yeah, you were right. I messed up there, Jason. So, would C be negative? Yes. Good call, Caitlin. The C would be a negative because I would subtract the 1400 over. So this should have been changed as well, but fortunately, that doesn't affect the fact that this was all 0. Okay, whether that's a positive or a negative. So I'm sorry for throwing you guys off. A lot of times I have my answer key out so I don't do something stupid like this, but it was kind of buried under some stuff and I wasn't paying attention to it. But a little bit of Avon calculus history here. This question used to be on my exam, and it was on my exam for years. And when I say years, guys, I'm talking probably about the time before you guys were born up until maybe shortly after you guys were probably in like elementary school. I used this for a long time. And I had students that do fairly okay with it, but I took it off my tests because you would never see a full-blown Newton's law of cooling like this on the AP exam. And it just didn't seem like it made sense to occupy that such large part of the test. So I said, nah, I was done with it. All right. Yeah, let's talk about why we get this 0. I had a question from Sam. And I want to try to explain it without using a calculator if at all possible. So let me get rid of some of the stuff that I did here. Let's break this down just little by little. So we are going to let t approach infinity. So this number t is going to get really big. So I have just this part here. If I focus on that, I have e to a super large number, right? Very big number. But it's not big in the positive sense, but it's big in the negative sense, right? Negative big number. Well, because we have a negative exponent, that means that we could reciprocate this, right? We could have 1 over e, but that doesn't change the fact that we still have a big number now as the power of e. And when I say big number now, I'm talking a positive big number, okay? Now, if you remember, from just our investigations in the first semester about 1 over really big numbers, we found out that those numbers tend to be very close to, oh, that doesn't help you, does it? But that is close to 0, right? Because this is scientific notation. So picture this decimal here moved over 8 times, which is going to produce, I believe, 7 zeros, right? So that's going to produce a number that's going to be very small, close to 0. And then because of that, this whole thing here is going to equal 0. And that's going to wipe out the negative 1400 multiplied by 0, just leaving you with that. Okay, so hopefully, Sam, that makes sense. So, yep. All right. All right. Before you go, I kind of want you to do me a favor, and if you can quantify this number in your head, this would be helpful to me. But I want you to compare. I know that this is only our second test, right? It's been a long semester, right? We're already, we're very close to the halfway point, right? We got a few weeks, but we've only had one test, right? Unit 6 is the only test that we've had. And it was a tough test. That was a tough unit. I'm really proud of how you guys came out. I want to know, how many of you feel better prepared for Unit 7 versus Unit 6? So just type better or worse in the chat. Do you feel better or worse? And if you say better with an exclamation point, that means you really feel better. All right, most of you have pretty good shape. Sam, not sure. Same, maybe. Okay. So I don't think too many people are saying that they feel worse, and there's no reason for you to feel worse. I really think that you guys are so strong with the majority of this. You're going to see so many familiar questions. So that's good to hear. I want you to go in having some confidence. So yeah, Johannes wants to look at 16 really quickly. I can do it, right? I got 2 minutes left. We can go over, but 16 is going to go really fast. I'm not going to make a big deal on the test this week about you guys remembering conic sections. I used to put this on the test. A lot of these problems were former test questions, but I think this is still a good problem in terms of just separating and integrating. Well, guess what? This equation, this differential equation, is already separated, is it not? So all one that has to do is integrate. So we can dive immediately in, integrate the left side, bam, integrate the right side, bam, and then, well, we don't have any initial conditions, so we're not solving for C, but we're trying to identify what kind of equation this might be. So if we play with this a little bit, maybe multiply through by a 2, we can do that, as my dog is chomping on her food nearby. We get y squared equal negative x squared plus c, and then if we add the x squared over to the left, maybe we put it in front, we have something like this. And then I ask you, does this look like any familiar equation that you've seen in your lives? Is it a circle? Hyperbola? Parallel lines? Really? Parabola? Or lines passing through origin? That can't be right. This is definitely a conic section. Well, it can't be a parabola because parabolas have only one of the variables squared. Turns out that it's a circle, right? Ellipse or hyperbola, sorry. Hyperbola would be the answer if there was a minus sign, either in front of the y squared or if the minus was like in front of the x squared, okay? Now, this is kind of neat. If I take away that minus sign and make that a plus x dx, reset the problem, which one is it now, guys? You can type it in the chat. Is it A, B, C, D, or E? If the equation was y dy equal x dx. Did I just blow everybody's mind? Is this solution going to be a circle, hyperbola, parallel lines, parabolas, or lines passing through the origin? Everybody get a chance to vote. Is Caitlin just by herself? Harsh's answer A was for the previous problem. I saw him type that in before I changed it. So Caitlin says B, she's right. Yeah, this would be a hyperbola. And it's because this x squared over 2 thing would be positive at that point, and then you're going to have to subtract it over, so it's going to result into that thing, which is a hyperbola. So again, you're not going to see any reference to conic sections because we just didn't discuss them enough. So, all right. Well, I am glad to hear that you guys are feeling better about this test. You should. I'm thinking that when the week is up, you guys are going to feel like your hard work paid off. I think this is the kind of unit that really does lend itself to you guys staying up with the homework, and it's not like Unit 6 where there's just so many different moving parts that it's easy to get lost really fast, even if you just like miss a day. So you guys are doing great. All right, really proud of you. So I am going to bid you all adieu, and if anybody has any questions tomorrow, just come on in the morning. I'll be in my room. Remember, I have Commons duty right at 7:45, so if you have a question really close to 8 o'clock, you can find me out there in the ALC Commons, okay? So anyhow, I wish you guys a good night, and we'll see you tomorrow. Take care.